Hi students, in this video we are going to cover colligative property. So this is a part 1. So there will be another part of this video. In this video we are only covering two properties, and in the next video we will cover the next two. So we are covering four properties in total. So let's understand this colligative property. It looks like a Colgate to me, but I don't know. So this word colligative actually means, it's a Latin word, root is Latin, and it means binding together, binding, right? Tying something. Like if you have a solute that will be binded together with the solvent, and what is its effect, what property it will change of the solvent. So that kind of introduction we need for this word colligative. Okay, so if you see the definition, you can see these properties. What are these colligative properties? These are the property of solution that depends on the number of solute particles. Remember this, underline this. So number will be important, number of solute particles, not their nature. So we will not get into what kind of solute is having a polar nature or it is non-polar. Okay, what kind of bonding it has, right? How much stable that is. So that kind of things will not come into the picture when we are thinking about colligative properties. When we are discussing colligative properties, we will only be concerned with number of solute particles, how many solute particles are there. And also, whenever we are discussing colligative property, remember that there's a major assumption here that we are going to use binary solutions. So there will be two components only, solute and solvent, and this solute will be non-volatile. Non-volatile. It will not evaporate, right? It will not contribute much, negligible contribution in the total vapor pressure. And this solvent will be volatile. So this we need to keep in mind when we are discussing these properties. So let's go for the first one. The first property which we are going to discuss is relative lowering of vapor pressure. We know vapor pressure, we have discussed while we were discussing Rolle's law also in detail. Lowering means it will get lesser, right? And a relative means relation to what? Let's think about it. So now let's see, this is was the pure solvent. So here it is pure solvent. So it will have some vapor pressure, and we can note it down when equilibrium has reached. And let's see, that is P naught. Okay, so I'm denoting it by P naught. Not we are putting it whenever we are talking about the pure form of something. So this is the pressure, vapor pressure, when it was pure, nothing was mixed. But now what you have done, you have mixed here. So this is the solution, right? So here's the solution. I have mixed some non-volatile solute. So that is important, right? So this is the non-volatile solute, non-volatile solute. So now if you see, the pressure contribution will be lesser, right? Less vapor will go. So the pressure will be reduced. So let me denote it by PS. So this is my PS, right? So if let's say, let's put some number, like if it is 20, the pressure is 20, now it will remaining 10. So it is lowered. So that is what the first term, lowering of vapor pressure, means. So we have lowered the vapor pressure because we have introduced a non-volatile solute. Let us understand. So let us say this is our solvent molecule, and this is the non-volatile solute. So it will not vaporize. It does not have any volatility, right? So it will not evaporate. But while we are making a solution, we have binded that together. That's what the word colligative, binding together. When we bind them together, they are holding down to each other with some force of attraction. And this force is what? Intermolecular force. Intermolecular force. And you can think like, because they are binded together now, they can act like a pair, right? Like they are together, right? They are held down with intermolecular forces. They are held together by intermolecular forces now. But now if solvent wants to get vaporized, this force will hinder it. This force will not let it. That's why they are getting less vapors in this case when we are making a solution of it. And what that will depend on? That will depend on how much solute you mix. Because remember, it will take more space here on this surface, and also the more binding will take place. So less and less vapors will come as you increase number of particles of no volatile solute. And just if you read this, you'll be able to get the formula also. Just read this. Okay, so first thing is lowering of vapor pressure. So it was something here, P naught, it has lowered to this. So let me write it down, how much it is being lowered. So it was P naught, okay, and minus PS, right? So that much it is lowered. So let's say, let me put some values, like it was 30 and 10. So how much we have lowered? 20, right? So that is what, here I'll put 30, here I'll put 10, and I will get lowering of pressure of 20. So these are just numbers to make you understand this formula. So lowering of pressure is done, and then the word here is relative. Relative to what? Relative to what was it before in the pure state. And that we know, we can denote it like P naught. like that, right? I've used here on the top, I can use at the bottom also. It's your choice. So this is what the relative lowering of vapor pressure. So above that, if you see above that, this part is what? Let me use a different color. This is a lowering, right? This is a lowering of vapor pressure. This much the vapor pressure is reduced. And what is this? While we are putting this in denominator, this is what it tells when we divide it. That is the relative thing, right? This is the word relative coming from. So relative lowering of pressure. Relation to what? Relation to what it was before. Comparing to that, how much it has been reduced. And it turns out to be, as colligative properties are only dependent on the numbers of particles, solute particles, it will be equal to mole fraction of solute. So here is the first colligative property. So what this formula says, a relative lowering of vapor pressure will be equal to mole fraction of the solute or number of particles of solute. So just to summarize what we have done, we have mixed some non-volatile solute and that got binded together so that the vapor pressure is lowered, right? And that lowering of pressure we can get like P naught minus Ps. What is P naught? I'm talking about P naught. Naught I'm using when we are talking about vapor pressure of the pure solvent. But now because there is something mixed, it has become solution. So that vapor pressure will be less. So the lowering of pressure will be P naught minus Ps. Now we find the relative measure. We will put in denominator what it was in the case of pure solvent. We will get a fraction, and that will be equal to mole fraction of the solute. So the second property is elevation in boiling point. So we'll be elevating or increasing. So elevation is a fancy word for increasing the boiling point of a solvent. So what we'll do, we will do the same thing. We will bind them, we'll colligate them, right, with solute particles which are non-volatile. And doing that, we can lower the pressure, vapor pressure, and the result is you will get higher boiling points now. So for that, we should understand this point very, very clearly. What is the boiling point? Boiling point is nothing but is a temperature at which vapor pressure becomes equal to atmospheric pressure. This is a new thing. We have not discussed atmospheric pressure as of now. We were just dealing with a closed system. So this is the first time we are going to discuss, but it will be fun. To understand boiling point, let's have water and a beaker, and I have a stove here, and I will start heating it. So what will happen as though, even when the stove was not there, it was evaporating, right? It has some vapor pressure, right? But now around that, there is nothing, there is no lid, right? So there will be some pressure of atmosphere, right? There will be some pressure, atmospheric pressure. So can I say that this pressure has become equal to this? No. So we'll note down when it becomes equal. So we'll raise the temperature from our room temperature. We will increase it, keep it heating. And at this point, 100 degrees centigrade, which we call boiling point, this pressure is so much, this vapor pressure is so much that it has become equal to the atmospheric pressure. Or you can say the molecules are ready to go. They can break this, right? They can break the pressure which atmospheres have built. So now they are ready to go beyond that, right? So that results in rapid evaporation. So the evaporation rate will be maximum. So you got the idea why water is boiling at 100 degrees centigrade. That is a benchmark actually when the pressure, vapor pressure which water can create is becoming equal to the atmospheric pressure. That's a benchmark. That's what we noted down. For water, it will be something. For different, liquids, it will be, different temperature where they boil. Okay, so we have 100 degrees centigrade. Pure water is giving us the equal vapor pressure which the atmosphere is putting us. And now I will play with it. I will put these red dots. What are these? They are non-volatile solute. Like you can think of like sugar, right? So now if they are binded together with water, now it is difficult for water molecules to escape. Their vapor pressure will be lesser. So even at 100 degrees centigrade, it can happen that they are not able to beat this atmospheric pressure. So even at this time, atmospheric pressure is winning. So what we'll do? We will increase the temperature. We will increase more kinetic energy of these molecules. And finally, let's say at 101 degree centigrade, they have the equal pressure as the atmospheric pressure. Now what we have done, see, we have elevated the boiling point of water. It was boiling at 100 degrees centigrade. Now it is boiling at 101 degree centigrade. So we have elevated by 1 degree here. Now we will discuss about the formula, how to calculate that, how much the elevation will be. So delta TB, so this is what delta means, change or elevation. In the boiling point, that will be equal to Kb. This is a constant multiplied by M. Remember, not X. So this M is molality. So let me use a different color for explaining this. So this M is molality. And what this Kb is, it's a constant. And we call it molal. We are doing elevation. So elevation constant. So this is a fixed value. It is found by experiments. And now what is a molality? Let's go with the definition of molality. It is nothing but number of moles. Number of moles of solute in 1 kg in 1 kg of solvent. So that is what the molality is defined as, number of moles. So remember, whatever the property we are doing, they are getting dependent on, they are relating with the number of particles. So here the molality comes, but molality, if you see, they are related to moles of solute, right? So if we want to write the formula of that, so that will be mass of solute, whatever the solute or how much sugar you have mixed. So that mass of solute, you need to divide it by molar mass of solute. Molar mass of solute. By formula, you can derive that. Yeah. So this particular thing, by the way, is how we calculate moles, right? This is what we are, number of moles, how we calculate. Number of moles. Okay. So we calculated number of moles, then we just need to take care of kilogram. So we'll just say 1000 here, and here we will divide it by mass of solvent in grams. So mostly it is, generally it is given in grams, so that's why it has been taken care of, right? So if it's not clear, it's grams, okay, in grams. And now let's write it thoroughly. So first thing is delta TB will be equal to KB, okay? And now in the molality, I'm putting all this stuff so that we remember it as a unit, as a formula. So that will be given mass, small w I'm representing. Then, 1000 will be multiplied with that, 1000, okay? Then divided by, what is the molar mass? Capital M, we can show molar mass of the solute, and then multiplied by what is the mass of solvent in grams, okay? Remember that this value is in grams. So please note down that this is capital W I want to show. So the mass of the solvent, I'm showing it by capital W. Remember that, okay? Don't get confused with the smaller one. This is for solute. And now there is one confusion which comes through this. So I wanted to clear that what delta TB will be, which minus which. And remember, what is this? This is always final minus initial. This is a change. Delta, we show the change. Final value minus initial value. So finally what we did? We made a solution. So the boiling point of solution will come first. And then minus, we will reduce it by boiling point of the pure solvent of simple water without sugar, right? Pure. So now think about it. We have made a solution and we elevated by 101, right? When we added sugar. What was in the pure sense, pure in the pure water was giving us boiling point as 100 degree. So if together I will calculate this, what we are calculating? We are calculating elevation in boiling point. So how much it is here? 1 degree, right? Right. So remember that sometime, this is a mistake, like which one is to taken where. So this will hopefully help. Thank you.